Yes, sir. Okay, thank you. So I'd like to first thank the organizers for this wonderful conference. I've learnt a lot. So I'm going to have a little bit lower energy. I'm recovering from, I don't know, some viral fever type of things. I only hit yesterday, so but I'll do my best. So is it good? So I'm going to talk about a different topic than what you've seen so far, but I'm going to connect it with all of these. My assertion is it's connected to digital earth in a fundamental way. So this is going to be on public health problems using computational methods for public health, and Could suggested I do an overview. So instead of going into specific results, I'm going to give an overview of this area and hopefully introduce you to some of the interesting problems in this and show you that it has all the right buzzwords of big data and everything. So hopefully you'll find interesting problems. I'm happy to go into more details like offline if you're interested, or I can send you papers and so on. So before I go on, I'd like to acknowledge collaboration with lots of friends and collaborators at Virginia Tech and in other institutes, and these are all the funding agencies. Okay, so I'd like to start with this fascinating account of role that epidemics have played in historical events, and I don't know, maybe some of you already know this, but I found it really fascinating when I first read this. So the point is, over the course of history, large outbreaks have contributed to significant historical events. The one which is most well known is the Aztecs. When the Europeans came to North and South America, they were not exposed to smallpox and other diseases, so that contributed to their defeat, is what it's believed. In the recent years, in the last 100 years, there have been several large pandemics. So one of the largest was this 1918 pandemic. So this was right after the First World War. Any guesses on like how many deaths happened because of the 1918 pandemic? No, order of magnitude of 50 million, and it was more than the direct deaths due to the First World War itself. So a lot more people died because of this pandemic than like the war and all of those events. These other pandemics, they have spread pretty fast. So SARS, so depending on how old you are, you would know one or more of these events. Okay, so the one most of you might be familiar with is the 2014 Ebola outbreak, where we saw these people with these yellow jumpsuits and masks because it was highly contagious. And of course, we've been interested in trying to control how diseases spread, and for the longest time we didn't have any idea of how the mechanics of these infectious diseases. So there's lots of magical cures and prayers, and one thing which people figured out was quarantining and social distancing always seemed to work. So this might seem mean, but like somebody who's sick, they would just separate them from rest of society. So like leprosy colonies was partly that. One of the interesting interventions was the precursor to the smallpox vaccine. So I don't know if you have heard of variolation. So the difference here is they used live virus instead of the vaccine would have attenuated pathogen. This one, they just took stuff from somebody who got smallpox, exposed other people to it, and it seemed to reduce the risk of infection. So starting from the smallpox vaccine 200 years back, there have been several major events in the development of mathematical epidemiology. So the smallpox vaccine was developed by Jenner. Like he saw these people who got infected by cowpox were not getting infected by smallpox, and so that gave him the idea of protection using that. One of the nice studies was the spread of cholera. So there's this work by John Snow. I'll come to it in the next slide. And in terms of mathematical models, the first one is for malaria by Ronald Ross. Many of you might be familiar with it. He used differential equation models to argue that by reducing the vector population, so reducing the density of mosquitoes, the disease is going to be controlled. We don't have to eliminate them, we need to get the density down. Is there a clock here? Let me just get my phone out. Okay, so one of the first examples of data analytics for like social good is this this work on cholera by John Snow. I don't know how many of you know about this. Since it's fascinating, I thought I'll take a few minutes to explain this. So this was in mid 1800s. So there were lots of deaths in London due to cholera. So John Snow was a physician and some like local administrator. So the first thing he did was he put these things on a map. So this was the map of London from that time. The blue dots are water pumps. And the red ones are the infections, the deaths due to cholera. The next thing he did was he figured out the travel time from each red dot to the closest blue dot, right? So this region consists of all the red dots which were closer to this blue dot than other dots, right? So what does this remind you of? Right, so this is a Voronoi diagram, and this was done like many decades before the notion of Voronoi regions came up. So from this, he concluded there was something wrong with this particular pump. This is called the Broad Street pump, and it turned out it had gotten broken and it was contaminated with sewage, which was contributing to this. And so John Snow said, let's close that pump, and that contributed to the outbreak ending. And then the other side effect was he figured out that water had a role to play in the spread of cholera. Till then they thought it was like miasma, bad air, which caused the spread of cholera. And what is the disease burden today? So infectious diseases are still the second largest cause of death, even though there have been so many advances in medicine, public health. Of them, respiratory diseases like account for a quarter of those. Yeah, so this is like the 1918 pandemic, which I mentioned. So what is the risk of such a pandemic occurring today? So the good thing is the 1918 pandemic happened because of a particular mutation in that virus, and public epidemiologists hope that, or expect or hope that such mutations will not occur now. And governments are much more prepared and coordinated. So the SARS and swine flu, they did respond. The Ebola is a different story, that they took a while to respond. But the other issue is even if you have a moderate outbreak, it becomes challenging. There's a shortage of vaccines and logistical issues. So if you've been following the flu outbreak, I don't know how many of you got infected. So there many cities in the US had shortages of antivirals and medical staff. So there were long lines in ERs. And and the other thing which is happening is modern trends are causing increasing the risk. So there's more travel, there's immunocompromised populations and urbanization. So more people are densely packed. Okay, so so I'm going to motivate the rest of the talk by going over the following. So what do public health analysts worry about today? So this is these slides are from the 2014-15 Ebola outbreak time. So this was a concern not just for like the public health agencies, but also lay public, because it seemed really scary that people would just drop dead with such a high probability. So what are the important questions which people were interested in answering? So some things about the incidence. So how many people have been infected? Where is the outbreak? So where all has it spread? So this is like a heat map of the West African countries, the color coded by incidence. So where did it start, and how did it start? And in the U.S., they were concerned. They were thinking about the risk of Ebola entering U.S. And there were questions: should we close all airports? So how do you answer that kind of question? How does this compare with past outbreaks? How contagious is the virus? So this is about the mechanism of the disease spread. So I'll just say a few words about the particular Ebola outbreak, and then we'll just move on to the more mathematical models. So it started in Guinea, and it spread because of bats, and the transmission was due to bodily fluids. So if you come in contact with the bodily fluids from some infected person, that would very likely cause an infection. And the spread was exacerbated by cultural practices. So West African countries, it was common for people to touch a body before it was I think buried, and that contributed to the disease spread. And so one of the big steps in the reduction of the disease was to change the cultural practices. And it took a long time because there was very little trust in public health agencies, and the public health infrastructure was severely damaged because of wars and all that. Okay, so so let's go to these questions. So all of these how, where, why, and all of those prompts for essays, and let's unpack those and see what it would take to answer those questions. Okay, so the first, when did the outbreak start? Where did it start? Who got infected? So this requires field work. So somebody has to go into that infected region, figure out how many people are infected or not, and that gets collected by agencies all over the world. So in the US it's CDC, and South America it's PAHO, and so on. Why is this hard? So this graphic is not very clear, but this is called the surveillance pyramid. So and this is particularly relevant for influenza, and you'll see why. So most people, in the case of influenza, when they fall sick, they don't go to any doctor, right? So they just stay home and take some fluids, and hopefully they get better. Some fraction of them go to a doctor, right? So all of these people who didn't go to for any consultation, they are not going to be traceable. Some people go to a doctor. The doctor most of the time just gives some medicine, but some fraction of them get some lab tests. Some fraction of them turn out positive because these tests are not very reliable. So you can see as you go up, there's loss in information. The ones which are collected by these reports are only at the top of this pyramid. This is going to be a really small fraction of the actual incidence. So we'll come back to this a little bit later. And if there are any questions, feel free to stop anytime. So the next set of questions is, okay, so this is still the same when, where, who, and so you can imagine this requires good surveillance. And so there are lots, so given that actual specimens from labs are going to be very few, there's a lot of interest in using open source surrogates. So people have used search terms, I'll come to that later, restaurant reservations, and interestingly TV watching. So any idea like how TV watching might be correlated to a disease outbreaks? Yeah? Huh? Yeah. Yeah. Yeah, Seymour, right. Yeah. So there is some work on getting some signal out of disease incidents from TV watching. So do a lot of binge watching and parking lot imagery and so on. So all of these are very qualitative. There's very lot of noise, so it's not easy to get a good signal for problems like forecasting, but it's used quite a bit. And in fact, there is this tool called Health Map. If you just Google for Health Map, you'll see this. They have an army of people, and they use automated and machine learning methods to extract incidence of disease from news, blogs, all kinds of sources, and they put them on the map. You'll see both like commonly occurring diseases and rare diseases. So this is and there are other sources. So it's a nice surveillance system. Okay, so the next okay, so yeah, so for these set of questions, basically it boils down to you need to get data on incidence. And this leads to nice problems in statistics and data mining and machine learning. So the next set of questions is about like how is it spreading and what kind of people are getting infected, and then more deeper questions like when is it going to peak. So the peak is important because that's so if you plot the time series of infections, the peak is like how many simultaneous how many simultaneous infections are going on, and that is the maximum load that might be put on the healthcare system. So the peak is really important. Many outbreaks die out on their own. So in order to answer these questions, you need models. So now we need data, and now we need models of how the diseases are going to spread. And one of the this part about when will it peak, it's related to this question about forecasting. So there's a lot of interest in forecasting the disease characteristics going forward. So to summarize, these questions basically require data and then models, and these models are complicated, so they need efficient algorithms and simulations. And then finally, this is what we expect of all our governments. How do we control it? So there are different kinds of interventions. There are pharmaceutical interventions, which are vaccinations, antivirals, or non-pharmaceutical interventions, which is if you are sick, just stay home. Typically, resources are limited. If you have enough resources, then these are not difficult questions. But almost always the shortage of vaccines, not enough hospital beds, and so on. So these now, so we need data, models, and we need good optimization tools. Okay, so now we'll talk about models for a little bit. You might have seen this quote by George Box. So it's even harder in the case of epidemic spread because there's a lot of uncertainty in the data that one can get, as you'll see later. So there are different kinds of models, and that depends on the possible roles, whether you're doing for prediction or for understanding, and so that determines what characteristics of the model you need to care about. So the accuracy or transparency and so on. Okay, so the one of the most commonly studied models is a differential equation based model. So each person is in 3 states: susceptible, infectious, or recovered. So you assume that the population is completely mixed. So they're like in this room in close proximity. So S, I, and R are fractions of susceptible, infected, and recovered people. And so this set of equations describes the dynamics in this model. So basically, the susceptibles decrease. So there is a quadratic term in the rate of decrease of the susceptibles and growth of infectious. So each susceptible and each infectious person can potentially interact because of this complete mixing assumption, and each interaction will cause an infection at rate beta. So beta is one parameter which is going to cause infection, gamma is another parameter which is going to cause recovery. Right? So in such a model, the epidemic is characterized by what is known as the reproductive number. So R naught, that's the ratio of beta and gamma. What can be shown is if R naught is more than 1, then there's a big outbreak, and if R naught is less than 1, the outbreak is going to die out, and that's easy to see. If you pull out I from here, you'll get beta S minus gamma, in the beginning S is 1, so almost everybody is susceptible. So if beta over gamma is less than 1, the rate of change of di dt is negative, and so the disease is going to die out. So such models have been used extensively. They are like one of the standard approaches that epidemiologists will use. They are simple, so you can solve it you can completely map out the dynamics, but there are problems. So like for SARS, it was estimated initially that R naught is like pretty high, so it's more than 2, and this was estimated based on like crowded hospital wards where it was initially spreading. But so going by this kind of estimate, SARS should have spread like all over the world and caused huge infections, but it didn't. Partly that's the limitation of this methodology, that people change their contact networks, and so those assumptions about complete mixing were no longer valid as the disease spread. So yeah, so the other yeah, sure. No, S and R. So the disease dies out when I becomes 0. So in fact, the following is true, that however contagious the disease is, R infinity, so the number of total infections will always be less than 1. It will be like some branching process, I think.
But if beta is positive, then there will always be some drift from S to I.
Right, but
R is an absorption state, everything is going into some gamma or whatever it's going.
Right.
So eventually, won't everything flow?
No, right, yeah. So even eventually, so basically the way you do that is you look at R infinity. So the end population for R. So that would be how many people like became infected and became recovered, right? So that will the solution to that. So if you take a ratio of like ds this fraction, this equation over this equation, I cancels out, and you'll get an equation for basically relating S and R. So from that, the disease dies out not when it dies out, you'll still have some people who never got infected in this particular model.
Okay, I'll ask you offline. I don't see it, but
Yeah.
And the second question is, so you mentioned so things like HIV, right? Where there's no recovery, you say you die if you get it.
Uh-huh.
So I remember 20, 30 years ago, people said everybody will be dead.
Right, yeah. Yeah.
So why isn't the species extinct yet?
Right, okay, yeah. So this model assumes a fixed population. So if you have to take birth and death into account, then there should be terms for in ds dt and dr dt. So there have to be terms to bring in birth and death. But the other issue in the case of HIV or any other disease is people change their behavior like as the disease is spreading, right? So the complete mixing assumption is no longer true, and so this in fact R naught is only reasonable in the beginning stages of the epidemic. Okay, so epidemiologists have recognized the issues with compartmental models, and so they've done extensions of these and so on. The one that we'll want to mention briefly is a network-based model, so because I would assume lots of you work on networks. So this is the SIR process. So there's an edge between two nodes. If they can come in contact and the disease can spread. So in this example, node 1 is infected, everyone else is susceptible. The disease spreads from this infected node to its neighbors with some probability, and the disease dies out when there are no infected nodes. So if they are only susceptible and recovered, the disease is going to die out. Okay, so if you want to use network models, then you need two things. One is you need the model for this disease probability, so the disease model, and you need a model for the network, right? So let's talk about network models. So there's a lot of work on random graph models, some of you, that we saw in the talk yesterday. So like this GNP and so on. These models capture local properties, so they can get you can preserve degree sequence and clustering and so on, but they cannot. So people have found if you run epidemic processes on these, they might have different characteristics than what you observe in real world. So this suggests you need to like model mobility in order to look to get good network models on which you can study diseases. So so there is a lot of empirical work in trying to collect information about mobility, and there's lots of interesting data sets. So one can use surveys, Wi-Fi, GPS, and call data records. They have different like advantages. You can start for that sample, you can get a good location of where people are, but it's hard to convert them into a mobility for the whole population. So you can collect call data records and things like that for smaller samples, and it's going to be like a static sample. So it's not possible to convert that into a network model for a population, which needs to take everyone into account. So modeling networks has similarities with this work on the case of internet graphs. So there's a lot of work in people wanted to know what is the structure of the internet router graph. So many of these random graph models were actually developed in that context. So like the Barabashi-Albert model was developed with that in mind. But then there's this interesting paper by Doyle and Willinger and others who said the internet is an engineered system, so it's not going to satisfy such stochastic properties. And so they suggested a first principles based method which takes the engineering into account. And we have done a similar thing. We use a first principles based method for constructing human population and mobility. So our goal is to figure out all of these characteristics for the population. So who's in that population, what kinds of activities they do, when they do. So these are activity sequences, where they do, and what is the characteristic of that activity. So you can imagine you cannot get such data sets except if like maybe you're NSA, or yesterday we heard Facebook. But all of us, we need to make models. So we have developed this methodology over a number of years, which takes like sensors, land use, and other data sets, makes a model for people and households. And so I'm sorry you can't read the legends. I'm going to quickly rush through this. It makes a model for where people in each household do different activities during the day, and the result of this step is going to have be a co-location model. So where are two people, which building is this person going to? From that you can figure out these two kinds of people are co-located for some time, and that gives you a conduit for the disease spread, and one can make a contact graph out of that. So this process combines a large number of data sets, both public and commercial, and some of them there are links here to if you want to download. So I'm going to skip. There is this work on dynamical systems on graphs, so that generalizes epidemic models, and the benefit of considering those is many questions about epidemic analysis can be mapped to standard questions you ask about dynamical systems. So I'm going to skip all of these and okay. So now recall those steps, the questions I asked in the context of the Ebola outbreak. So these are the steps that would that public health agencies would deal with. So we talked about data, we talked about disease models, models of the population and the network, depending on whether you're using differential equation methods or a network. Those become pretty complicated, so you either use simulations or analyze the contact graphs. These issues about prediction, calibration, and so on they become really challenging for such models. So these are spatiotemporal, and so computationally they're really hard. Once you have all of these, then you can do what public health agencies would call situational assessment. They can do forecasting. Is it going to be a big outbreak, and when will it peak, and design interventions, and so on. So in the next few slides, what I'll do is just go into a few of these steps and just tell you some of the problems that come up. They're interesting problems from different areas, from math and computing, and hopefully you'll see the flavor of these problems without seeing necessarily any detailed results. Okay, so one of the basic problems is inference. So the problem here is you know some components of the dynamical system. So maybe you know the graph, you know some infections. You want to figure out other components. So one of the most basic problems is source inference. So you know some infections, you want to find out the source, where did it start, and that's often referred to as patient zero. This graphic is about the HIV outbreak. So people were interested in figuring out how did it spread into the US. So there was some person who transmitted it, and so they did sequencing of all of the infections, and they blamed this guy. He was a flight attendant, and he's numbered 0. And I read recently that it was not him. It was, I think it's not fully resolved. So that's the source inference problem. There are other questions. So if you know some infections, you want to figure out the remaining ones. Or if you know something about the contact network, but you don't know exactly. So let's say the network is parameterized. So you know something about what infections have happened. From that, you want to figure out the right contact network or its parameters. So all of these come under inference problems. And people have come up with different kinds of formulations for each of these. They're all extremely hard problems. So for instance, source inference, there are many different formulations. So like likelihood maximization, and choosing a source which such that the infections are as close to what you've observed, and this one based on a description length. The next set of important problems is surveillance and detection. So we cannot hope to like monitor everyone. So the question here is, can you monitor some strategic people or collect data in some way so that you can figure out characteristics of the disease just from your surveillance set? Right. So there are different problems here. So the sensor set problem is, can you monitor a small set of people so that from the states of infection states of those people, you can figure out about the disease. And there is this nice empirical paper by Christakis and Fowler. So they say, and they did this in Harvard, I think. They pick some random set of people, and they asked they asked those people to find their most popular friend. So they pick these popular friends of a random subset. It's a small subset. And they keep periodically asking them whether are you sick or not. So this blue plot is the infection state. So the time series of infections. So this is time. This is number of infections. The blue plot is number of infections by time, just restricted to this subset that the surveillance set that you pick. And the red curve is the time series of infections in the whole population. Right. So what they were able to find is the peak happens. This gives you an advanced indication about the peak. So the peak happened like a couple of weeks, or maybe a week before it happened in the population. So monitoring some strategic set of people gives you a lot of information. This problem is generally open. It was empirical. They don't say anything about. You can formalize this as a nice optimization question, but it's like it doesn't have any nice properties, and so it's okay. So let me. Okay, so the next big area in that real-time epidemiology loop is forecasting, and I'll talk a little bit about influenza. So remember this surveillance pyramid. So the data that you can get, which is about actual positive cases, that's the top of the pyramid, and there's very little of it. So this raises the following question. So what can we really forecast? So if you're trying to forecast influenza, right? So you cannot hope to forecast the actual number of infections, right? Because you don't know, a lot of them are in this bottom part. So what can you really forecast? So the thing which, so CDC is in this business of trying to forecast, and they run these forecasting challenges. And so what they ask for forecasting is this quantity known as percent ILI visits. And so this is what it means. So they get a few physicians to report how many patients they are seeing and how many were have influenza-like illness symptoms. So these are basically like you have fever and you have some cough or this. So all of those are clubbed under influenza-like illness symptoms. So they're called ILI. So there's a network of like some 3,000 providers who give information on how many patients I've seen, what fraction of them were ILI positive, and the CDC converts that into a fraction for the whole country, and they want to forecast this quantity, percent ILI visits, right? So this is a well-defined problem because now there is a ground truth you can get from these providers. And this graphic, this from a few weeks back for this for different flu seasons. The red one is this year's flu season. This was before it peaked, at least in the US. Now it has crossed the peak and it's going down. So the problem of forecasting influenza is can you figure out this percent ILI time series? Can you forecast it? So can you say how many infections, what is the value of this time series, let's say 2 weeks ahead, and what is the peak going to be, and so on. So this problem is interesting because Google tried to do this. So how many of you heard of Google Flu Trends? Yeah. So then you would know everything associated with that. So, so this is the formal problem here for the flu forecasting. You have some time series of percent ILI visits till some time t. For the next week, you want to figure out what this quantity, right? So Google's idea was very simple. So they said, let's try to look at search queries. So they have everything that you search for. From that, they look at what fraction of the search queries. So if they are making a forecast for Kharagpur, what fraction of search of general search queries were ILI related. So they have a methodology for figuring that out, and then they make a linear model for predicting ILI visits by the fraction of search queries which are ILI related. Yeah. So this paper got a lot of publicity. This was like 2008, 2009. The black one is the real time. The black one is Google Flu Trends, and the red is the real incidence, and it was tracking pretty well. But then people so then it turned out it's there are lots of problems. It didn't work well for many seasons after that. And you can imagine if you're doing this, there's an obvious flaw with this, right? If you're doing forecasting based on search queries, if people get worried and start searching more, it will give you a false indication that there's more flu going on. And there is this nice paper which it has a very provocative title as well. I'm going to skip all of that. So what I'll okay, so maybe I should just briefly mention the problems in this. So this was my title, controlling epidemic spread. So the goal here is, you know something about the network, initial conditions, and the disease models. You want to design interventions for controlling the epidemic. So you want to choose whom to vaccinate and so on, and there are different objectives. So if you're in a SIR model where the dynamics is governed by the R naught, so you can try to reduce R naught by reducing transmissibility, so people can start using face masks or like better hygiene, or they can improve recovery, so increase gamma. So I'm going to skip all of these things, and actually maybe in the time that I have left, I'm going to. Okay, so let me come to a conclusion, and then I just want to show you a demo of a simulation tool that's available. So public health is like a really important area, of course, and it has all the buzzwords of big data, and so this graphic was made when these 4 V's was in vogue, and I understand it's not. I need to update the graphic. So these are really hard problems. So how is it connected with at least my interpretation of the theme of this conference? So if you want to model and forecast diseases, you also need, so you need multiple things. One of them is a good models for the environment. So there are models for influenza which use humidity. So you need that, but that's an easy thing to get. Waterborne diseases, they use like mapping of water bodies, and like vector-borne diseases, same thing. So the new thing I want to put out is, in addition to all the infrastructure mapping that we've heard, one needs to also consider user representation. You need to consider where people are and what are they doing to really understand the impact of all of these future risks on human populations. So let me just, if I have, so maybe I'll take 2 minutes and just show you one tool. So this is, if you, else I'll maybe I guess we can share the slides, so you'll see the link there. So this is a tool that like a cyber environment we built for public health analysts to run different kinds of studies. So we have many populations. I don't know why it's so there should be a, I'm not able to see the full screen, so you can, there's a button on the right where you can set up a study. So basically the populations I mentioned, many of them are in this tool. You can set up different kinds of analyses. Yeah, so you can set up a new experiment. So let's say so you can, you want to do this analysis in some region. So there are many different regions, populations that we have, including one for Delhi, if you want to use that. So you can set the population. Then you have to, so remember, the population model requires, like an epidemic model requires many things. So you need to specify the disease model, initial conditions. So you need to specify the disease model. I'll just pick something that I have here. Then you have to specify initial conditions, and there are, so I'm not going to, so these are fairly intuitive. The thing which is not so intuitive is intervention. So this tool is used by now like analysts from different agencies for trying out different kinds of interventions and seeing what is the risk and what is the benefit. I'm out of time actually, so I'm going to end by, so you can, so there's a button which shows different kinds of, so you can get like a, this shows like a cumulative time series of infections. I'm out of time, sorry, I'm over. I'm going to end here.
Hello.
Yeah.
Actually, the problem with this SIR model, because according to SIR, simultaneously a susceptible node is converting into infected node, and infected node is converted to recovery node. But it may be possible that there is some delay in conversion from susceptible to infected and infected to recovery.
Right, so those can be easily added. So in fact there is a duration for which somebody is infectious, right? So there's a rate, the gamma parameter captures that rate for becoming recovered. So somebody can, it's not simultaneous. Somebody can be in the infectious state for several days, for instance. So for flu it is like 4 or 5 days.
Another problem is like in case of Zika, there are some spatio-temporal parameters should also be included.
Right.
Position is always changing.
Correct. Yeah.
Environmental condition is also affecting on that.
Right. Yeah, so absolutely. So I haven't talked about vector-borne diseases. They are much more complicated. The kinds of models people use are called metapopulation models. So these are spatiotemporal models where you have a like a compartment for each. Let's say you're doing it for each city. So there's SIR states for each city, and there's mixing between cities, which comes because of the interaction between the vector and people who can spread the disease. Okay.
Sir, you talked about cholera, Ebola, there are several outbreaks, and after these outbreaks, people came out and studied and what happened. Like in cholera, 585 people died. And
Right.
in Ebola, around 10,000 people died. And then people came and make studied and find out some solutions. So basic problem is that as you found the source of the disease, it would be great to solve the society. But and again you talked about forecasting the outbreaks. But particularly in India, you talk about Uttar Pradesh, I am from UP, and specifically in Voronoi, where we are having a disease encephalitis, and it is till around 100 years, and till now we haven't found a solution, and around 10,000 people have died. So I just wanted to know that although it's not relevant over, I think.
No, that's yeah.
Know that what the system is doing, what we are doing in India. We talked about London, and after the death of 500 people, system waked up and they took some measures to find out some solutions to that. But I think no, we are not focusing the problem in that. Until unless you reach to US, you are not going to study it and something like that not happen until unless US is going to be affected by it. So just I wanted to know that what would be the good way to sort out these problems.
So these are like really hard problems. For some of them, the mechanisms are not fully understood. So there's challenges in coming up with good models. The other thing, almost always, like social distancing will work. So if you can keep the infected people away from the ones who are not infected, it will stop the disease spread. That's not possible in today's society, right? So that's partly the in terms of interventions. If you don't understand the mechanisms, these are not very implementable interventions.
But I think we need to come up with solution on this problem.
Right, yeah. So it's a question for you.
If a study can be done on cholera, then why not in encephalitis?
Sure, I think that's right. I think that's a very good question. I don't know how to do that, and I think that's a good problem.
No, I think so.
Probably can we have this
Yeah.
line where it makes use of
Okay.
of time. So any more?
Yeah, I have one question if you allow me.
Yes.
I'll unplug by then. Okay.
So, you are talking about public health, right?
Yeah.
Yeah, you are talking about public health.
Uh-huh.
But if you really look at it, last 30 years, the whole epidemiological change has happened from communicable disease to non-communicable disease.
Uh-huh.
Right? For example, in India, in 1990, there were 25% of the deaths were because of non-communicable disease.
Right.
There were 60% of the communicable disease. That actually has reversed.
Uh-huh.
57% versus 24%.
Right. Uh-huh. Yeah.
So what you look into is the communicable disease.
Correct. Right.
So is there something which we can use in the non-communicable disease also?
So that's yeah.
There are a lot of challenges in it.
Correct. Yeah. So there are. That's a really important question. The methods are different, and people haven't figured out. So they don't know how to. Yeah. There's a lot of interest. Yeah, sure, yeah. So I just want to, one comment I'll make is people have found like many of the non-communicable diseases also have peer effects. So like if friends have smoke then or have obesity, then this person might is more likely to be obese, and they use some methods like that, but it's like not figured out.
Yeah.
Thank you.
Next time, Prof Anil.
Oh, thank you.